All right, should be up and functional now. Apologies everyone for the delay in this. I'll get this uploaded as soon as I'm able to. A whole bunch of factors as to why. One of the primary ones was as class was starting on Wednesday, this happened. So just remember that office buildings are not in fact Taurus proof, Ford Taurus proof. So maybe we should revise some building codes accordingly. Also, when this happens to your immediate neighbor in an office building, it's the Christian thing to do to go help them, make sure they're alive. It's the little things. Nobody was hurt, unfortunately, including the chuck wagons who decided to turn our office building here into a drive-through, which was not really on the development plan. Right as I went to start class, police and fire and things and helicopters and reports and I will be giving a few grace days accordingly on the assignments that are due. I'm not going to bother updating the due dates right now because it's more important for me to focus on making sure that you have some lesson content to go with what we were going to cover. The core of which is going to be the development of algorithms and what that looks like. So we're going to switch to screen share, and I'm going to go to full screen on this because it will make life quite a bit better, or it'll be a little bit easier. So I'm going to switch to screen share, then go to full screen for this. Try and keep you guys from getting motion sick from the infinity mirror effect. So things to be mindful of are you're going to be focused on a couple key aspects of what's going on. I'm not going to focus on the video content, some of the other things. The important things here are you want to clearly, as you're starting to think about an algorithm, you want to clearly identify, going back to this, what is an algorithm? You specify the problems, you analyze the problem, you design the algorithm to solve the problem, you implement the algorithm as a program, you test and verify the completed program, and maintain an update. That's the kind of software development idea. So analyzing the problem, you need to understand inputs. So what data can you work with? Outputs, what result am I after? And any additional requirements and constraints for how all of this is going to work. What are limitations, hardware processing limitations, all sorts of things. And then when you start to develop the algorithm, you want to start by listing steps from beginning to end. So we're going to walk through some exercises here. Something about breathing in all kinds of extra dust and insulation. Pulling glass out of your hands, all kinds of stuff. Make sure that you remember when people decide that we need to legalize more drugs, that this is the kind of thing that it results in. So maybe don't. Just some words of experience there. All right, so list the steps from beginning to end. Beginning is step 1. Have a specific step to end. Then don't try and solve every single little detail at first. Start from the top down and break it into sub problems. Solve each of those individually, and then you kind of like outlining a written paper. You're not trying to write and revise and edit yourself as you go, or you'll never get done. Then you use what's called pseudocode to kind of combine it and then kind of desk check the algorithm to see, is this a thing that's going to get to the result that I'm looking for, or is it not? Okay, so having said that, you're going to convert the algorithm to a program, and we'll walk through kind of an example, and then we'll take a look at, with the Circuit Playground Express, how that operates and what that looks like. And I'll probably pause and do some of the last bit of typing and editing and things and make that all work. Try and shave down the length of time of the video as much as reasonably possible. So in converting this to a program, you're going to implement the flowchart and pseudocode as a program. You're going to verify that it compiles, troubleshoot spelling errors and capitalization issues and number agreement and all of those sorts of things. Verify that the math is correct, etc. Test some boundary conditions. And doing that sometimes requires intentionally entering erroneous data. And then if the program behaves unexpectedly, pause, back up, double check the algorithm, double check the program, modify those, and then there's debugging tools and techniques. We're going to learn more of those as we go through the semester. Identifying the variables is very, very important. The variable types and how we store that data is important. So there's levels of things that we need to understand here. In a program in general, the compiler is going to put memory or put variables and the values associated with those variables into memory in a specific way. So each of these data types used in the algorithm need a name, and I've been trying to train you guys already. Use a name that means something. Don't do Bob's your uncle, because that doesn't help you. Do something that is meaningful. Red LED 1, things like that. Left switch A, whatever. Use meaningful names that you know what they're coming from, so that you can troubleshoot more easily, so that you don't have to troubleshoot your names and then troubleshoot the code. It's too many steps, you'll never get done. Integers are common data types, so 0, 1, 2, -53, whole numbers, integers, very useful. Decimal numbers have to be stored differently, different data type, different memory requirements. Scientific notation, same kind of deal. There's some limitations there. Character strings, those are things that are in C++. They're going to be a little bit different. We'll talk about some character strings. We will use some of that in some of the code that we're going to be doing, so that you are familiar with that data type and how to use it. But we're not going to focus on all examples of that. So a simple example is something like, how would you convert miles to kilometers? So the problem statement, identify the problem. We need to convert a distance in miles into kilometers. Okay, fairly straightforward. Identify the input. We have a name, dist in miles. And then we're going to store that maybe as a decimal number. Then we need to identify the outputs, dist in kms, kilometers per second, or kilometers in this case. KMS is probably not kilometer. Don't do KMS because that would be confusing. The decimal representing the distance in kilometers. So these are the data types. We've got our inputs and our outputs. Okay, great. Now what do we do? Break it into steps. We need an input, dist in miles. We need an output after we convert. So we need some math step in the middle there. Step 2 is not really precise because it's not specifying how to do the conversion, but that's part of the reason why this is not really a complete algorithm yet. So when I'm going to grade the assignment, for instance, I'm going to be looking specifically for how do we have enough steps and enough detail that you clearly know what you're doing. You clearly have an idea what your approach is going to be, but not so little detail that like you have a magic box, convert something into something else. Solve problem is another example of like, no, that's not something that you can implement. If you're putting in boxes that say solve problem, insert magic here, easy bake oven, and then like, no, that's not what this is about. So it's not yet a complete algorithm. So we need to break it up further. What's the formula for step 2? 1 mile is approximately 1.609 kilometers. Number of miles can be converted to kilometers by multiplying by 1.609. So the formula is distance in kilometers is distance in miles times 1.609. So you need to make sure that the variable names are the same here. So input dist in miles, convert dist in miles to kilometers. How does that work? Substeps. So problem, input, substeps, output, close program. Multiply distance in miles by 1.609. Put the result into, again, I would not use KMS because reasons. Kilometers, it's already plural. Don't need to pluralize a thing that's already plural. This algorithm gets the task done. It's not super duper user friendly, so we need to add some additional helps in there. So how does that look? What does that result look like? So convert miles into kilometers is output. Please enter distance in miles is output. Input distance in miles. So these first two are asking for an output, printing to a screen. In this case, we're going to use a couple examples of a screen in order to make this work as efficiently as we can. And I'm going to, I want to make sure we can. I'll make sure we can make edits here because it'll make life a little bit easier. Okay. A couple things will make life a little easier mechanically here. So the output is printing something to the screen, enter distance in miles, printing something to the screen. Input, so we take input from the user, then we do a math step, then we do an output, distance in kilometers is, and then output distance in kilometers end. So this, a good algorithm, requires some effort and some attention to detail. You don't just throw it together and it works. You have to think a little bit through. So we're going to look at some examples of how to print stuff out and ask for input through the semester. We're going to do a lot more of this, but you want to start thinking in terms of what does a program do? A lot of times it's going to prompt you to do something. This is one of the steps that you want to take to do that. So output, we're going to say in order to list numbers less than 10, we're going to output list of numbers less than 10, put 1 into the number, output number, add 1 to the number. If the number is less than 10, go back to step 3, output the number, add 1 to the number. It's less than 10, go back to step 3, end. So this algorithm has no inputs, only one variable called number. So it's a very straightforward little tight example of how something is, how value is grown inside a loop in code. Don't inhale fiberglass. It's really not good. Yeah, not good. Also, don't crash into buildings or do drugs. These are things I shouldn't have to explain to you guys, but don't. So this is another example of how something is grown inside a loop. That's very simple. So an algorithm that lists odd numbers less than 10, output would be list odd numbers less than 10, put 1 into the number. If the number is even, skip to step 5, add 1 to the number. If it is not, if it's odd, output the number. So that's step 4, add 1 to the number. If number is less than 10, go back to step 3, end. So step 3, question here is that sufficiently precise? Is this a useful algorithm? You could make an argument that, well, sure, it makes perfect sense. No, it's really not. So how we could improve that is same for 1 and 2. 3 becomes, if a number is divided by 2 and then it has a remainder of 0, go to step 5, output number. If it doesn't, so it has a remainder, go to step 4. Step 5 is add 1 to number. If number is less than 10, go back to 3. So 3 is a math check, and it's an actual step. How am I going to do this? So it's a comparison, and that's what I mean by a comparator. We're going to talk more about those as we go to implement them, but this is to start getting you guys to think about this in a different way now. So flowcharts are an important part of this, and it's something that you want to include because of the way that this works. Beginning and ending shapes in flowcharts are really going to help make this process a little more clear in order to make this work a whole lot better. So these shapes are used to begin and end these bubbles with the arrows. They're ovals. They're always ovals. They are not diamonds. They are not other shapes. They are very specifically shaped in order to denote beginning and ending. So you have an algorithm name, then you have a word end that is at the end, signifying you're done with the processing. Now you can see why I didn't record this yesterday. Okay, fine. Rectangle has 1 entry and 1 exit only. This is a pseudocode example for text. So it's some kind of action that's 1 step in the algorithm. There's a diamond shape that's a decision point, yes or no, +1, +1 or 0, yes, no, true, false kind of thing. And that's simply it. Ask a question. If yes, go this way. If no, go this way. This way we understand how things work. Selection, value to select. Then there's a tree with multiple branches, and you have all of this up and running in order to make this all work correctly. You want to make sure that you have those different branches because of the way that these values are going to operate. So there's also a connector shape. So A goes to A on some other page typically, or connection on the same page. This can be used for. So the shape shows connecting point from one to another. Those are stitched together in your algorithm showing, hey, we ran out of room, but we have to show you what we're doing from this output. Then it's used as the input to the next steps. Fairly self-explanatory. Off page is these home plates. These are used for multi-page flowcharts. This can get to be pretty common for much larger processes. The shape shows the destination of the connection. Visio is a good example of how to use this. There's another site called flowchart.io. That's the one that I'm probably actually going to have you guys use rather than installing Visio and trying to do all the things and get school to pay for a bunch of licenses and blah, 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 stuff that's never going to happen, right? So the shapes are actually going to combine to create these structures. So the straight line structures, there are single-sided branches, there's double-sided branches, there's selection structures, there's until loops, while loops, and do while loops. I'm not going to spend a ton of time on the loop structures yet. There are some instances where we're going to be using some specific loops. We're probably not actually using a do while loop this semester, at least if memory serves. So straight line structure looks like this: action, then next action, then next action. Pretty straightforward, not surprising, not something. Single-sided branch, action, question, evaluates yes or no. Branch action happens or it doesn't. Branch action happens, then it brings it back to the same action afterwards. Double-sided branch, yes or no, goes to an action over here if true, an action over there if false. So these two are indeed different. The branch action happens only if the yes is triggered. In the no case, the second action or the third action happens without a second action in the single-sided branch. Double-sided action, question, true action or false action, then that proceeds to the third action, whatever that is in the algorithm. So again, makes sense. It'll especially make sense when we go to start doing applications of these. That will help tremendously. So the selection structure, where you've got multiple value outputs for values to select. You have an action for 1, 2, 3, and other action values. Then it goes to another step. So all branches have to converge together at the other end. A do while loop asks about repeating again. We're not going to be using this one. We'll come back to that later. The while loop, that is something that I think we are going to be using a little bit. We're definitely going to be doing a lot of work with loop structures. The while loop specifically has some advantages for its specific condition. So there's an initial setup, then it says, do I perform an action? Yes or no? Yes, then action to repeat. Then it's a loop increment. So we're looking to see, does this have another example? Let's add another piece to this puzzle. I'm telling you, breathing fiberglass that somebody has just strewn all over the air is really bad for you, just in case any of you wondered. Sorry guys, I'm trying. An example of this: initial setup. There's 12 cookies on the plate. Perform action, loop action. Do I eat a cookie? Yes. Then I eat the cookie. Loop increments again. There's still cookies on the plate. Do I eat a cookie? Yes. Action repeats until I eat all 12 cookies, and then there's no more cookies. So while there are cookies, I eat them. While there are not cookies, I don't eat them. That's how a loop action happens. Stuff that probably you do in normal daily function without really thinking much about it. An until loop is a little bit similar, but again, we're not going to be breaking out into an until loop for the things that we're working on. So we'll go into a couple more examples. So count to 9. How would we do that? So here's an algorithm in pseudocode to output numbers 1 to 9. So we print list numbers less than 10, put 1 into the number, output number, add 1. If it's less than 10, go back to step 3. Once it reaches 10, or it would reach 10, it goes to end instead of printing out the next number, because the output happens before we're doing our reference check. So once we've added 1 to the number in memory, we don't print it out unless it's less than 10. So 10 doesn't get printed out in this algorithm. The flow chart looks like this. List numbers less than 10, output list of numbers less than 10, put 1 into the number variable, output the number, add 1. Is the number less than 10? Yes. Then go back to output number, add 1 to number. Is the number less than 10? Yes. Go back, output number, until it reaches a certain level. So while the number is less than 10, it continues to output number, add 1 to number, output number, add 1 to number, compare, output number, add 1 to number, compare, output number, add 1 to number, compare, until it reaches that threshold. Once it says, okay, I'm at 10, I am no longer less than 10, no, end program. Odds less than 10, output list of numbers, list of odd numbers less than 10, put 1 into the variable number. If number divided by 2 has remainder 0, go to step 5, and that's add 1 number. Otherwise, output number. So we're going to have to use one of those decision trees here. If number is less than 10, go back to step 3, end. What does that look like in a flow chart? List odd numbers less than 10. Output list of odd numbers less than 10. Put 1 into number. Divide number by 2, and put a remainder in the variable rem. Is rem equal to 1? Yes. Output number, add to number. Is yeah, great fun. Is remainder equal to 1? Yes. Output number, add 1 to number. Is remainder not equal to 1? Then add 1 to number. Then it's comparing. Is number less than 10? Yes. Go back up, divide it after it's been increased, go back, divide it by 2, and put the remainder into remainder. Is the remainder 1 or 0? Depending on the answer, we either output number or we add 1 to number. Either way, we're adding 1 to number. So all paths through this loop have to add 1 to the number. If this output number came after this step, after the add 1 to number, for instance, there was some other action, this loop would never complete. It would be broken because it wouldn't reach this condition if this output number bypassed and didn't come to the same action of adding 1 to number, because otherwise your increment would be wrong. So it couldn't actually end, it would get stuck, and that's what we call an infinite while loop. So while number is less than 10, do this stuff in the middle. All right. Yeah. So I think we've got a couple more things. I'm going to switch to one other, I think, slide set, and then we can take a look at what this looks like when we implement it using the Arduino specific language, which I think will really help because that'll make life a little easier on us. All right, the class time now, where we would normally be doing things, is there would be a lot of back and forth examples of you guys trying to do pseudocode with some specific examples. So what I'm going to do is I'm going to link to another YouTube series that was done by Dr. Kordowitz, who helped to develop the revision for this course. This will help kind of guide you through the examples of, or kind of guide you through from another perspective, what the pseudocode looks like, how that operates, and how that can be translated into Arduino speak. And so what we're trying to focus on here is making sure that you guys have what you need in order to start developing the concept of pseudocode and what an algorithm looks like. How do you structure this? How do you make these things work? How do you do the flowcharts? How do you do all of this just stuff in order to make sense of the coding? There's some other videos out there. I think he's got a whole series on a bunch of these that I recommend you guys take a look at as a point of reference. So I will link to those as well. I'm going to walk through an example of what the algorithm looks like for Blink. So I'm going to type that out real quick and then come back to it in just a second. All right, so here is the example of the Blink algorithm converted to this format for easier viewing. So you start by naming the output pins. So that's what we did. We set up the pins to output. We turn the output on, pause, turn the output off, pause, and then return to step 3. So those of you that haven't completed this step need to go ahead and complete your initial program. This is pseudocode, and it's important to understand why this is different from the regular code. I'll put it next to it. The code looks a little bit different. There we go. Oh, what kind of nonsense that's got going on. So here, the code looks like it'll do capitalization here, but I'll see if I can undo a little bit of it. Integer LED pin equal 13. Suppress output or go to next line. Set the pins to output. So setup loop. Pin mode 13. 13 output. Go to the next line and close. Turn output on can't be done until you do loop. So this is actually our void loop. Let's see, yeah, turn output on. So digital write, LED underscore pin, make sure capitalization is the same, I. Next line, digital write, I'll include the weight here in just a second. Digital write, so we'll do our pause here. Delay 250. Next line, digital write, LED in low. Next line, delay 250 milliseconds. Next line. Okay. So our code and our pseudocode do not look the same. So our void setup is our code for how do we actually do the setting pins to output. So we're not looking for you to immediately jump to the next step. Fun. I'm really serious about this. Don't breathe fiberglass or do drugs. They're bad for you. Our setup and loop run the things that we need to run. This pseudocode is a lot easier for us to read and understand, and that's why we want to start here and then learn how to implement it here. I'm not asking you to start just automatically understanding how to write it here directly, because that's not reasonable. So instead, we want to name the output pins, set the pins to output, turn the output on, pause, turn the output off, pause, return to step 3. This is a reasonable algorithm. There is enough detail in the steps, and this is the way that I want you guys to start for your algorithm for this next assignment. So this is what will help you kind of get from here in the pseudocode over to here in the actual code as we go to understand it. So we'll get a lot more practice on this. It'll make a lot more sense when we're all done. But I want you guys to get some practice in with this. And again, I'll link in the announcements to the additional video series for some of this content, but this is the core of the actual material. So go back and review this again. I told you I'd try and keep it as concise as reasonably possible, but this is the concept. We're trying to master pseudocode right now so that we can develop algorithms in pseudocode, so we can start translating them into Arduino using the 3 key steps. We initialize our variables. So int is not initialize, int is integer, but it makes it easier for you guys to remember. Initialize the variables, set up the variables to do what we want them to do, output or input, usually. It's really your 2 options. Then loop is where you do stuff. Okay, so do the stuff with the things you set up in the loop. That's what the loop does. So we're going to get you guys to think about this and how to make sense of all of this so that it's reasonable. But this will help start guiding your thinking on this is how we do it. This is how we operate. This is how we run. So I'll try and get caught up on questions as I'm able to. I know there's going to be a lot. So I'll try and catch up on messages. because I think I'm already drowning. I think there's like 60 or something crazy. So we'll find out. So you guys have a good rest of your weekend. Again, I'm going to try and see if I can get in, adjust dates. I don't know yet. And then we will reconvene next week. All right. Other than that, have a good weekend.